Hi all. Welcome to this video, and here we are going to just extend what we have already seen earlier about the contiguous memory allocation, where we talked about fixed partition scheme in the last lecture. In this lecture we are going to talk about the variable partition scheme. So let's talk about variable partition scheme. So in fixed partition scheme, we have the partition of the main memory as fixed. We already partition the main memory into certain fixed size block, and it remains the same throughout. And the problem we faced with that partition scheme is internal fragmentation. Let's see about how variable partition scheme eliminates internal fragmentation and what is the benefit of using variable partition scheme over fixed partition scheme. Okay, so as the name suggests variable, here we don't have any memory block fixed. So we have one chunk of memory, and it is a continuous chunk of memory. So instead of dividing into fixed block or fixed partition, we have a continuous chunk of memory which is undivided. Okay, so now how does the division occurs, how does the partition occurs? Whenever a process comes with a particular memory request, let's say 50 kb, so what happens that when this process comes to this contiguous chunk of memory, this 50 kb is allocated to this process and the remaining remains as it is. So now this process occupies 50 kb of space and is placed into this chunk. So this partition is being made with the incoming process P1. Okay. Now let's see another process P2 comes, and P2 comes with a memory requirement of, let's say, 350 kb. Now this 350 kb will be made available in this contiguous chunk of memory, and again with this 350 kb is allocated to P2 and P2 resides here, right? Again, let's say another process comes P3, and P3 requires 400 kb. Now this 400 kb will be allocated in this continuous chunk of memory after P1 and P2. We have P3, and P3 occupies this 400 kb. Don't go with this picture, I draw it smaller, but actually it's 400 kb is 350 kb and is 50 kb. Now let's say after P3, P4 comes, and P4 requires 200 kb. So this 200 kb will again be allocated from this continuous chunk, and this P4 will be placed here. Okay, then after that P5 comes, and let's say P5 occupies 150 kb. Now for this P5, 150 kb will be allocated from here, and P5 will be placed here. So now all these processes have been placed into this memory size, and now we have this memory as divided into this undivided memory gets divided into partitions like here 50 kb. Then we have this after P2, this chunk is 350 kb. After that we have this as 400 kb. Okay, then 200 kb. After that we have this due to P5, again this memory gets divided into 150 kb. So from a continuous memory like this, I mean undivided memory like this, it gets divided with the coming of the processes. Okay, now so this is the way in variable partition scheme it is divided, the partitions are being made. So initially what will happen, initially memory will be single continuous chunk of memory. Initially memory will be single continuous free block. So where is the free block? This is a single continuous free block. So this is the initial case. After this, whenever the process comes, according to the size of process, the process gets accommodated and the partitions are being made accordingly. Okay, so the next statement with this is whenever a request is being made by a process, whenever request being made by a process, Accordingly, what happens? Accordingly, the continuous chunk of a free block, okay, it gets divided or it gets partitioned. Accordingly, partitions will be made, right? Partitions will be made. Now, let's see what is the problem with this, whether internal fragmentation gets eliminated with this or not. Definitely, with this, we have this internal fragmentation getting eliminated. Okay, so let's say this is our large memory initially. Okay, I'm sorry, I'm not able to draw it in a very clear way because it gets curved. Okay, let's try. Okay, now let's say P1 is a process occupying 50 kb. It comes and it gets occupied here. Okay, P1 gets occupied with 50 kb, right? Then let's say, so this 50 kb partition is made in this continuous memory. Then again P2 comes, and with P2, P2 requires 350 kb, and again we have a large chunk of memory left. So this P2 gets occupied here with 350 kb, right? So this 350 kb partition is being made here. Then P3 comes and P3 requires 400 kb. And for this 400 kb, again we have this partition being made as P3, and 400 kb is allocated to that. So the partition being made is of 400 kb here. Now P4 comes and P4 requires, let's say, 200 kb. Okay, so again for P4 here, partition is being made with 200 kb. Okay, and this 200 kb partition is being made for P4. Okay, now P5 comes, right? P5 requires 150 kb, and for P5 again we have made this partition here, and P5 is getting accommodated into this, and this is 150 kb. Okay, let's say after that P6 comes and P6 requires 250 kb. Now in the remaining memory, we have some space left, so we will allocate P6 here, okay, with 250 kb, giving it space of 250 kb, and this partition is being made. Now let's say P7 comes and P7 requires 70 kb. Okay, now in this remaining space we will be allocating P7 to 70 kb, and the 70 kb partition will be made for this. Now P8 comes and P8 requires 300 kb. Now let's see, we have this much space left. If it is 300 kb, then we will allocate P8 here. Okay, let's say this space left is 300 kb only. So we will allocate this P8 here, and 300 kb partition will be made. Okay, now we have consumed the entire continuous space, and let's say we have another process coming up, that is a P9, and that requires 100 kb space. Okay, so for this, will it be able to accommodate into this? No, because already the partitions that is being made are previously occupied by existing processes. But we can accommodate this into any block if we if any process goes into waiting state or gets completed. Let's say this P4 gets completed, so we can accommodate P9 into here, right? Let's say in this 8 process, the very first process that goes into completion is P1. Okay, so when P1 gets in outside, like P1 is completed, okay, then this space will remain empty. Okay, now let's say if we have this space as empty. Okay, now we don't have here P1, and this 50 kb is empty. Now for this partition, can we accommodate P9 here? So P9 requires how much kb? 100 kb, and we have the partition made of 50 kb. So we can't accommodate P9 into here. So this space will remain unused here. Until and unless we won't get a process of occupying 50 kb, we can't accommodate P9 here. Let's after P1, let's say P7 gets completed, because we do never know na which process will get completed first. So let's say P7 gets completed, so this place again remains vacant. Okay, when P7 is completed, this place is remains vacant. And if we want to accommodate this P9 into this space 70 kb, again it becomes unused because P9 requires 100 kb and this is 70 kb only. So with this limitation in the size, we can't accommodate P9, right? So all these unused space, even though the process requires this space, but we can't accommodate, we can't join these two space together and accommodate 100 kb, because altogether we have total 50 plus 70, that is 120 kb unused space, and we can't use this space to accommodate this process, right? Because all these both are in different partition, right? So this is called, we give this unused space a term called external fragmentation. This is definitely not internal fragmentation. This is external fragmentation, because although we have this space left, we can't use the space and allocate any process to the space, right? So the problem with variable scheme is external fragmentation comes into picture. Variable partition scheme brings external fragmentation. Okay, so we have the space left, but we can't accommodate the processes. Okay, there is one more thing that we need to discuss about this. Like, let's say if only smaller processes keep on coming. Okay, there will be one M. Then what happens? Suppose we have all the processes completed in the earlier part, but we have the partitions being made as 50 kb. Okay, 50 kb. Then we had a partition being made as 350 kb. Then we have a partition being made as 400 kb. Okay, then we have the partition made as 200 kb. So this is based on the earlier. Let's say all the process gets completed, and these partitions that are already being made as remains as usual 200 kb. After that we had 70 kb and 300 kb. So 70 kb, and then we have left as 300 kb. So these partitions are being made. And let's say if only smaller processes keep on coming, let's say, let me change the pen. Let's say we have a process coming as P10 requires, let's say, 15 kb or 10 kb. Okay, so in that this 10 kb is occupied, remaining is unused. Okay, so 10 kb is being utilized by P10. Again, we have some process coming as 50 kb like P2. So P2 occupies 50 kb, right? Again, we have some process coming as P3, and P3 requires 20 kb. Okay. Then we have some process coming as P4. P4 requires 10 kb, like that. So in this way, we have some smaller processes coming up, and they require certain smaller amount of space. So what is happening? This space, this space, this space, all space remain unused. Okay, so these unused space are actually remaining because of we have all those smaller processes that is being coming into picture. Okay, so what happens that when some smaller processes keep on coming, then the larger partition will be made into smaller partition. Then larger partition is made into smaller partition. Okay, we have actually, this was actually 50 kb, right? But since this 10 kb came into existence, so this 50 kb got divided into 10 kb and 40 kb. Now let's say we have another process coming into 50 kb, so we can't accommodate that 50 kb process here, so we have to again divide this into 50 kb and this 300 kb left. So in this way we are just the space got unused by the incoming smaller processes. right? And the larger partition is divided into smaller partitions. So this is one problem of also external fragmentation. So external fragmentation is comes up in variable partition scheme, okay, and internal fragmentation comes up in a fixed partition scheme, okay. So to avoid the external fragmentation, we have followed certain features to avoid external fragmentation, following techniques can be used. The very first is compaction, okay. So in compaction, what happens that we just move all the processes in one direction. Either we move all these processes upfront like here, or we move all the processes in downward direction so as to make space for the new processes. Because fragmentation, external fragmentation only happens when we can't use the unused space, like that happened in the very first example. Okay, so we already had 120 kb space, but we were not able to use that 120 kb space here, right, for a new process of 100 kb. Okay, so either we can, or in this process also we already have some unused space left where we can't accommodate new processes coming. So what we can do, that we can compact, either we can shift all these processes above or we can shift all these processes down. So this is called compaction, also known as moving all the processes, moving all the processes towards the top, towards the top, or towards the bottom, towards the bottom, to make space for the new processes. Okay, to make space for the new processes, right, so that we can have available memory for the incoming processes. But it could be, it is not so much easier, because obviously if you are moving the processes upward or downward, you have to change the addresses of the process, which is uh, not suggestible when the processes are in running state. Okay, so compaction is the process of moving all the processes towards the top or towards the bottom, so as to make space for the available for the new processes in a single continuous place. Okay, in a single continuous space is important. So this process is known as compaction. But again, there is a side effect of this compaction, because compaction is undesirable. Compaction is undesirable to implement, as it interrupts with the running process in the memory. Okay, because it interrupts with running processes, running processes in the memory, right. Second, we need to know how to implement the non-contiguous memory allocation, because whatever we were talking about is the contiguous memory allocation. So there are some problems like internal fragmentation and external fragmentation, both with variable and fixed static allocation, fixed partition scheme. So we need to implement non-contiguous memory allocation. Okay, so as to avoid internal fragmentation or external fragmentation, right? So this we will learn in the next video. And also we need to learn about some of the partition allocation method, which is a part of this fixed or variable contiguous memory allocation. So this we will learn in the next video. So till that, keep watching, and do like, share, and subscribe if you like this course. Thank you very much.